Hi all, I'm Kemi Kong, your chemistry teacher. Welcome to Tiger and Cat channel. If you like this video, please do remember to subscribe, like and share. Today we are going to discuss about metallic bond and boiling point, melting point for elements of group 1, group 17 and period 3. You must remember, explain the melting point and boiling point of the element in terms of type of bonding and intermolecular forces.
5 in chemical bonding, metallic bond. So for this chapter, right, we are going to learn about the formation of metallic bond, the properties of metal, and then the factors that affect the strength of metallic bond and the relationship between metallic bond and boiling point. Okay, first, we must know what is metal. Okay, as we know, right, metal is shiny solid at room temperature, except mercury, because mercury is in liquid form. So anyone can give me the example of metal? Sodium.
Aluminium.
Aluminium, yeah. Aluminium more near to us because we always say the construction using aluminium. Okay, and then copper. Okay, copper used for ferrum iron. Okay, with characteristic high melting point and density. So the bond between the metal, right, we call it as metallic bond. If the question asks you how to explain metallic bond, actually it's the electrostatic forces between the positively charged metallic ion and the sea of electron. So this one we can represent it by using a diagram. This diagram we call it as electron sea model. So you can imagine, so the fierce is the atom of the iron, and then the blue dot is the electron. So the blue dot represent the delocalized valence electron. And then the fierce with positive charge is the positive ion of the metal. Okay, this is in general view. Okay, in a metallic bond, metal atom can be imagined as an array of positive ion immersed in a sea of delocalized valence electrons. You check this diagram. This is the arranged orderly because metal is solid. That's why they arrange closely and orderly. Okay, form an array of positive ion and then immersed in a sea of delocalized valence electron. So the sea localized valence electron is a blue dot. Hey, please check who have didn't mute your microphone. Mute it first. Thank you. Okay, so these delocalized electrons are not bound to individual atom. What means by that? Meaning that this free electron is moved around. It's not belongs to any of the positive ion. It's just moved around. And they can therefore serve to bind a large number of metal atoms together.
One of the properties of metal is malleability. In Malay, is mudah ditembak. Means it's the ability of a metal to be hammered into shape. Able to hammer into or press into shape without breaking or crashing. The second property is ductility. In Malay term is kemuluran. Is the ability of a metal to be drawn into wire. Okay, when any stress is applied to the metal, right, you can check through this diagram. One layer of the atom can be slide over without disrupting. So for example here, after slide over, right, okay, here still like electron sea model, the metal ion still immersed in the delocalized electron. Okay, actually ductility is a measure of a material ability to undergo significant plastic deformation before rupture or breaking, which may be expressed as percent of elongation or percent area reduction from a tensile test.
In the array of solid immersed in a electron sea mode, the free electron, still the same. So they still can conduct electric and conduct thermal. So these two other properties of metal: good conductor of electricity, good conductor of heat. Okay, the explanation mainly due to the free electron. The mobile electron can move around. So you check the explanation. When an electrical potential is applied to the metal, the mobile electron will move towards the positive terminal and thus conduct electricity. Because electron is negative charge, that's why we move to the positive terminal. Okay, for thermal conductivity, when one end of the metal is heated, the kinetic energy of the electron increase. This we know. Okay, when heat applied, okay, particles, the kinetic energy of the particles will increase. Same for electron. So this is then transmitted to the other end of the system of delocalized mobile electron. Okay. Okay. Next. Okay. Factors affecting the strength of metallic bond. This part very important. So we have to know the strength of the metallic bond depends on two factors. The first one is the number of valence electron, directly proportional to the number of valence electron per atom. Okay, due to the delocalized valence electron involved in the formation of metallic bond. Second is the radius of the atom, inversely proportional to the size or radius of the atom. This one we learned during chapter 3. Because when size getting smaller, okay, the strength of the bonding getting stronger because the nucleus and the valence electron, their distance is closer. So we check, okay, by using the example of sodium, magnesium, and aluminium. Sodium 1 valence electron, magnesium 2, and aluminium 3. Therefore, the melting point and boiling point of sodium is the lowest, and then next is magnesium, then the highest is aluminium. Okay. Let's check for this diagram. Here is period 3. This is period 2. As I say just now, okay, this one valence electron, 2 valence electron, 3 valence electron. 1 valence electron, 2 valence electron, 3 valence electron. Aluminium has the highest number of valence electron, and then the size of the aluminium is the smallest. That's why you check the melting point and boiling point compared with magnesium and sodium is the highest. Okay, now one question I want to ask about boron. Why the melting point and boiling point for boron is higher than aluminium? Both of them are group 13. Okay, 3 valence electron. But why boron is higher? Okay, so this one I call Hozin. Why? Why the melting point and boiling point of boron is higher than aluminium, even though both of them are group 13?
Because the size of boron is smaller compared to the size of aluminium.
Yes, you are right, exactly. Because boron in period 2, and then aluminium in period 3. Okay, boron and aluminium we compare in terms of principal quantum number, means the number of valence shell. Boron only has 2 valence shell, and then aluminium have 3 shell. Okay, good. Okay, so you all have to understand the situation. Okay, next. Okay, we go for exercise. The first question will reference to the structure, lattice, and bonding, discuss the electric conductivity of magnesium. So, you have to mention that the positive charge surrounded by the sea of electron, where the electron itself is delocalized. Delocalized means move around, okay, can free to move. So, freely move freely, and said to be conducting electricity. Actually, right, when we explain about the boiling, the conductivity or the conductivity of electricity or conductivity of the thermal, right, we must mention the electron is delocalized and move freely. And then next, you have to explain by using the electron C model. Okay, just now the electron C model is in general view. This one is in specific view. Okay, 1 magnesium 2 plus with 2 positive. Why 2 positive? Because release 2 electron. If you notice, right, for this electron C model, there are 8 magnesium ion. That's why total there are 16 electron. Because 8 times 2 equal to 16. So there are 16 electron. You must label magnesium ion, and then you must label the delocalized valence electron. Okay, finish. Now please look at your tutorial question 6. Okay, question 6. Everybody, please take our tutorial. Look at question 6, chapter 4.4. Describe the metallic bond in aluminium by using electron C model. Okay, how are you going to draw the electron C model?
The diagram.
Yeah, we have to draw the diagram. Very good. Okay, so actually, right, the diagram have to be the same. You just need to change. Okay, all the magnesium over here become aluminium. But what is the charge for aluminium?
3 plus.
3 plus. Yes, aluminium is 3 plus. So you change over here aluminium. Yeah. So aluminium. Okay. And then must change to 3 plus. Okay. So I have to copy paste. Okay, all here. Copy. So here become aluminium 3 plus. Okay, this one become aluminium 3 plus. Any question do you want to ask me related with this diagram?
Madam, for the describe question memang wajib must draw.
Depends. Sometimes no need. But I think this diagram is quite simple, right? You actually no need to draw eight aluminium ion, you know. As long as you can draw the solid phase. Okay, for example, for this, I will try to draw 4 only. I can draw 4 only. As long as when you draw this diagram, right, must look like solid. They arrange in orderly. Okay. And then you must tell you must tally the number of electron with the valence electron. Okay, for example, aluminium 3 plus, right? So total how many electron is based on this diagram?
12.
12, yes. 4 times 3 equal to 12. Double check. Okay, 12 is enough. So you just need, okay, you just make the box smaller. And then don't forget, you must label. Okay, because I copy and paste over. You must label. Okay, this one is aluminium ion. Okay, must label aluminium ion. And then this is all the delocalized valence electron. Okay, and then you make the box smaller. Okay, so this is the answer for 6A. Okay, 6B. Explain why the boiling point of calcium is higher than the potassium. Kiranish, why? Why the boiling point of calcium is higher than potassium?
The strength of the metallic bond is proportional to the number of valence electron,
And
and the radius of atom is inversely proportional to the strength of metallic bond.
yes, the first point you must tell me the general statement. Directly proportional to the number of valence electron per atom and inversely proportional to the radius of the atom. But you haven't answered the question yet. This is just general statement. So you have to continue by
Comparing the element, is it?
yeah.
Potassium has only one valence electron per atom, whereas calcium have 2 valence electron.
Okay, good. Then one more.
So the strength of metallic
Nope.
bonding.
Nope. The size of
Size of calcium is
is smaller than?
smaller than the potassium atom.
Yes. Okay, good. So, okay, the point is you have to explain. Okay, the number of valence electron of calcium is 2, whereas the number of valence electron for potassium is 1. So the number of valence electron of calcium is more than potassium. At the same time, the size of calcium is smaller than potassium. So as we know, the strength of metallic bond is directly proportional to the number of valence electron per atom and inversely proportional to the radius of the atom. Okay, yeah? So you must give the general statement and then explain both factors. Any question?
Madam, the
Yeah.
radius can assume as the size of the atom.
Can, no problem.
Okay, thanks.
Okay, any question about metallic bond? If no, right, we proceed for the next. Ada apa-apa soalan tak? Okay, if no, right, we proceed for this one. Okay, next we are going to discuss about the boiling point of group 1, group 17, and period 3. Okay, you check for here, right? What is melting point and boiling point? Melting point and boiling point of a substance is a reflection of the strength of intermolecular forces holding the particles together. Because if the strength is strong, means the boiling point and melting point is high, or vice versa. Okay, you look at this diagram. Group 1, alkaline metals. Group 17, halogen. Okay, when going down group 1, you check the melting point and boiling point, what happened? What happened?
Decrease.
Yes, decrease. Okay, we look at group 17, halogen. Chlorine, chlorine, bromine, iodine. When going down the group, what happened to the melting point and boiling point?
Increase.
Increase, you see? Okay, as we learned before, right, when going down the group, right, okay, the size of the atom increase because due to the principal quantum number increase and then the shielding effect increase. This what we learned before, right? Okay, so the strength getting weaker. But in this case, group 1 is metal, group 17 is non-metal, halogen. Okay, the structure is different. Okay, that's why the trend is different. So we have to be careful when answer this kind of question. This you learned already during secondary school chapter 4 periodic table. So now we revise a bit. Okay, this is a comparison for group 1 and group 17 when going down the group. Okay, as we know, this is alkaline metal, this is halogen, and then the structure is different. Group 1 is metal, group 17 is non-metal, halogen. So for halogen, have simple molecular structure with strong covalent bond, holding the atom together in the molecule. Okay, for group 1, just now we learned already, they are metal, so metallic bond. Here, so the strength of the metallic bond is depends on the number of valence electron and the size of the atom or the radius of the atom. So the decrease is due to the decrease of the boiling point and melting point is due to the proton number of the element increase, which means atomic radii size increase. The outermost electron are further from the nucleus. This is for group 1. These cause the attraction between the nucleus of the atom and the valence electron in the metallic bond to be weakened. Okay, this is totally exactly same as we learned in chapter 3 periodic table. So as a result, the melting and boiling point of the element decrease down the group. Okay, ini kita belajar dulu. Nucleus dengan valence electron jauh, ikatan lemah, jadi tak kuat, i.e. rendah. i.e. rendah means, okay, senang remove electron. At the same time, in this case, okay, the melting point and boiling point is going decrease. But for group 17, okay, the simple molecular structure having the intermolecular forces we call it as van der Waals forces. Okay, if you have watched my video before, van der Waals forces is depends on the number of electron, and then the number of electron is based on the size of the atom or molecule. Okay, when the size of the atom or molecule getting bigger, the number of electron increase. When the number of electron increase, right? Okay, the polarizability of the molecule increase as well. Okay, this one you have to go through my video when the Waals forces are okay between the neighboring molecule getting stronger. As a result, the melting and boiling point of the element increase down the group. Okay, so be careful. Group 1 going down the group, melting point, boiling point decrease. But for group 17, the simple molecular structure with strong covalent bond, and then the intermolecular forces named as van der Waals forces, it depends on the size. So when the size is bigger, the strength is stronger. Okay, the van der Waals forces is stronger. So going down the group, the melting point and boiling point increase. Okay, this one is for group 1. Okay, first IE decrease, that's why melting point, boiling point decrease as well because easier to remove the electron. Okay, this is for group 17. Okay, increase boiling point, increase melting point when going down the group. Always remember, group 17 exit as diatom. Okay, because the valence electron is Ns2 Np5, group 17. If you want to achieve the noble gas configuration, they have to share electron. So fluorine share one to form one bonding. So this is covalent bond. Okay, in order to achieve noble gas configuration. Alert, fluorine and chlorine are gases at room temperature, bromine is liquid, and iodine is solid. Okay, I think you're quite familiar with this diagram because I use it to explain during chapter 3 as well. Okay, when across period 3, what happened to the melting point and boiling point? Okay, if you still remember, right, last time I asked you, you need to use how many point to explain this part? The answer is 3 because sodium, magnesium, aluminium under one category, which is metal, and then silicon under metalloid, and phosphorus, sulfur, chlorine, argon under non-metal. Okay, before I proceed, right, I want to ask some question. Finas, are you here, Finas? Okay, soalan madam ialah sodium, magnesium, aluminium. Which metal has the highest boiling point?
Aluminium.
Why?
Because valence electron of aluminium is greater than sodium and magnesium.
Yes, and then?
And then aluminium, size of aluminium is smaller than magnesium and sodium.
Yes, you are right. Okay, you check. While you explain this, right, you must explain what type of bonding. So, sodium, magnesium, and aluminium are metal, strong metallic bonding. And then next, you must explain what type of forces. So, this forces is attractive force, okay, between the positively charged metal ion and the delocalized electron. Then, now you have to mention, okay, the strength of the metallic bond is directly proportional to the number of valence electron and inversely proportional to the size. That's why, okay, the smaller size, blah, blah, blah. Okay, the more electron, blah, 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 stronger attraction. Okay, now you explain in detail, sodium 1, magnesium 2, aluminium 3, and then the size, okay, decrease from, so again, mention aluminium has a stronger metallic bond. Okay, next, Natasha. Natasha? Natasha, are you here? Natasha? Okay, I changed. Shafika. When I call your name, don't keep quiet. Just answer. Never mind. Yeah, Shafika, aluminium and silicon, which one higher? The melting point.
Sorry, madam. Aluminium and
Silicon. You look at my slide, the answer will be on my slide. Huh? Sorry?
SI.
Aluminium, silicon. Yang mana? Yes, very good. Si. Si has the highest boiling point and melting point. Why? Tengok apa yang saya highlight kat screen tu.
Silicon.
Ya, I tanya why? Ya, silicon. silicon has the highest melting point among the element in period 3. Why? Tengok sini, apa jawapan dia? Tengok slide, madam dah tunjuk jawapan dah, cakap je.
Because it
What happened to you?
have
Yeah. Betul? Giant covalent structure. Okay, yes. Thank you, Shafika. This is
It
because
has
silicon has a giant covalent structure.
giant
And then each silicon atom is bonded. Yeah, giant covalent structure. Yes, you are right. It's bonded to 4 other silicon atoms in tetrahedral arrangement. And then a large amount of energy is required to break the strong covalent bond between silicon atom and the giant covalent structure. Okay, next question. Phosphorus,
Silicon
sulfur, chlorine, and argon are non-metal. Okay.
I think her internet is slow.
Yeah, I also think so. Okay, thank you. Okay, Rose. Soalan seterusnya. Rose, are you here? Rose? Okay. Phosphorus, sulfur, chlorine, argon. Among these 4 non-metal elements, which one has the highest boiling point? Okay, as we know, there are simple molecular structure with weak van der Waals forces. If we check my previous video, van der Waals forces depends on molecular size, molecular mass. So the higher the molecular mass, the stronger the van der Waals forces between the molecule. Among these 4, which one has the highest melting and boiling point? Okay, if we check, right, phosphorus, sulfur, chlorine, and argon are non-metal. Okay, we cannot compare with atom because we are talking about the molecule. So phosphorus as cis molecule in P4, sulfur in F8, chlorine in diatomic Cl2. Okay, so argon is as monoatomic. The covalent bond with the molecule are very strong, but the van der Waals forces of attraction between the molecule are very weak. Okay, maybe some of you will confuse. Okay, this one also explained in video van der Waals forces. Please do remember check my video. Okay, you look at this diagram. The bonding between sulfur and sulfur atom. So S8, right? Between it is covalent bond. The intramolecular forces between the sulfur atom is covalent bond, which is a strong bond. But the molecule of sulfur S8 and with another sulfur S8, here is van der Waals forces, which is a weak bonding. Okay, that's why these sentences right now, the covalent bond within the molecule are very strong. So between the S atom and S atom are very strong. But the van der Waals forces attraction between the molecule, the S8 versus S8, okay, is a weak van der Waals forces. So the van der Waals forces of attraction increase as the molecular size increase. If you check, definitely S8 has the highest boiling point, then followed by P4, then chlorine. Argon, as at the monoatomic, is the lowest one. Okay, so this is the molecular wave. Okay, S8 is the highest. That's why sulfur has the highest boiling point. Van der Waals forces is proportional to molecular size, or we can say is relative proportion is directly proportional to its RMM. Relative molecular mass, relative molecular wave is the same. Okay, you must always remember the periodic trend in the melting point of a substance depends on the type of intermolecular forces or bonding involved. So we check one more time. Okay, for metallic bond. So directly proportional to the number of electron and inversely proportional to the size of atom. Okay, you have to check. Okay, this is the electron C model of magnesium 2+ ion. Okay, positive metal ion and then C of electron. We keep on checking the study about the electron C model. You must know how to draw it. Arrange in sequentially, in orderly, and then look like solid. Okay, they are close together. So this is the blue color is the factors, and then this point is the details. Okay. Strong metallic bonding, electrostatic force. Please highlight. You check when I explain the slide, right? I'm using different color. So it's the different important point. So please highlight, please underline, and then jot down the key point. Okay, for part 2 about the silicon giant covalent structure, covalent bond. Okay, holding the atom in 3-dimensional array. And then one silicon can bonded to another 4 silicon atom. So it will form a tetrahedral covalent bonded, okay, to others 4 silicon. And then high energy is needed to break the strong covalent bond. Okay. This is in 3-dimensional view. Okay, for part 3 is the non-matter. So it's simple molecular structure. What type of forces? Van der Waals forces. And then the van der Waals forces is depends on the molecular size. When the molecular size increase, the strength of van der Waals force increase. That's why if check the molecular waves, S8 molecule is the largest one, followed by P4, chlorine 2, and argon. That's why the melting point, the highest one is sulfur, and then the lowest one is argon. Okay, that's all for here. Okay, always remember how to explain. Must know how to explain. So this is the answer scheme. This is the answer scheme. You have to check. Sodium is metal, and then silicon is metalloid. Here is non-metal, and then this one is metallic bond. This one is covalent bond. This one is van der Waals, simple molecular structure. Okay, this one is metallic bond. This one is metallic bond. Attractive forces between the positively charged metal ion and the delocalized electron. Okay, how to explain this one? This one you have to explain giant covalent structure with strong covalent bond as well. Tetrahedral arrangement. Okay, this one we'll explain in terms of simple molecular structure when the Waals forces depends on the molecular size. Clear?
Clear.
Okay, good.
Hope you all learned something. Thank you.